So at this point, we're going to start to explore more complex data structures such as graphs and trees. And before we do that, it's a bit helpful to understand a little bit of graph theory just to help ground these data structures and help you understand some of the fundamental ideas related to them. So in this video, I'm going to talk to you a little bit about the general idea of graphs, how they work, and how they're structured. A graph contains two things: a set of vertices, or nodes we may call them sometimes, as well as a set of edges. The idea is that the vertices, or nodes, represent individual items, and the edges usually represent some sort of relationship between those items. So I'll give you an example of this using a simple idea, which is a computer network. On a computer network, we may have a bunch of different computers, and we can represent all of these computers using like these circles like this, and we would call each of these individual ones our nodes, right? So each of these different circles is a node. Now, if I wanted to represent the fact that computer 1 is connected to computer 2 on the network, I could draw a line between them. We call this line an edge. So this is the main idea here. So we have different nodes, which are the general items, and then we have connections between those nodes, which represent the relationships, in this case, that these two computers are connected on the network, right? And we can have really any number of connections between these. In this case, every computer is connected to every other computer on the network. So we have a variety of different edges connecting all of these computers together. And that's really the main idea of a graph. It just represents a relationship between different items using circles to represent the different items, or what we'll call nodes or vertices, and then edges, which are lines between each of those different nodes or vertices, right? And at this point, you may notice that this really does look similar to the node-based data structures that we were talking about earlier in the course, right? In those sorts of data structures, we essentially had items, and they were connected to each other, right? And they were connected to each other, and the connection was representing what came next in the sequence in this case, right? This too could be looked at as a graph, where each item is an individual node in our graph, and there's an edge between two items if they're connected to each other. So really, we've been working with the idea of a graph up to this point. We just haven't called it that because we didn't really need to introduce any of that terminology. But now at this point, when we could have, multiple different connections between things, so we don't necessarily have just like a linear sequence, but maybe multiple different connections, it becomes helpful to make this a distinguishing factor between the idea of, a graph and, anything else. So this is a really basic example of a graph. This is something that we would call a simple graph. And there's a few main things that make this graph simple. So the first thing that I'll note here is that these edges don't have any sort of direction. And what I mean by that is what this basically represents is that computer 1 is connected to computer 2. Also, computer 2 is connected to computer 1. So this edge goes in both directions. The connection is, going both ways. But what we could do is we can actually add an arrow to this. And what that would represent is that the connection only goes one way. So computer 1 is connected to computer 2, but computer 2 is not connected to computer 1. This becomes known as a directed graph. The graph now has a direction associated with it, and that's going to represent, that things go in one direction, but not necessarily in the other. If we wanted something to go in both directions, we can add an arrow to both sides of the edge like this. This would then represent that the edge works in both directions, right? So we can have things either going in one direction or we can have things going in both directions, right? And that would represent the idea of a directed graph. So basically, a graph can either have directions or it cannot have directions, right? So those are the two main distinctions that we have. Now, there are a few other interesting things about graphs. So let me just draw out a new graph so I can show you some different ideas here. A graph isn't limited to just having one connection between each of its different nodes. So in the example that I showed, I had something like this, right? We could actually have multiple edges connecting two nodes, something like this. We could also have an edge connecting a node to itself. We call this a loop. And the idea of a loop can really vary based on the application, right? So maybe in the example of a network, it may be like a loop-back connection, right? Something like this. But we'll see loops sometimes pop up inside of problems in terms of this sort of edge that starts in one place and ends at the same place, right? When we have edges that are multiple edges between the same node or edges that are self-referential, This is something that we need to account for often inside of our algorithms, whether these things exist or not. We often refer to these kind of graphs as multigraphs. So a multigraph could have multiple edges between nodes, or it could have self-referential edges. So this is another important idea to keep in mind. So we've seen this sort of idea, which is a multigraph. We've then seen a simple graph, which basically has no multiple edges. We've also seen the idea of an undirected graph. So this graph right here, which has no directed edges. All the edges are, both directions. And then we had the idea of a directed graph where all of the edges had directions to them. So these are the different sort of ideas that we've seen so far with our graphs. One final thing that I want to introduce here, and it will make this idea of a multigraph make a bit more sense, is that edges can have weights associated with them, or costs. So if we take a look at our idea of a network, for example, there may be multiple connections between two different spots in a network, right? So this one might be, connection A, this one might be connection B, and there may be multiple different ways of getting from A to B. Maybe this one takes 10 milliseconds, maybe this one takes 50 milliseconds, and maybe this one takes 70 milliseconds, right? So that's why we may have multiple connections, is because they may have different times or costs associated with them. And a pretty common problem in graphs is going to be trying to find the fastest possible way to get from one point to another. And in those sorts of situations, we may need to account for the cost associated with each edge in order to find, the lowest cost way to get through, the fastest way to get through, something in this sort of nature, right? So these are some basic ideas around the representations of graphs. And I bring this up now primarily so that I can contextualize the idea of trees, which we'll talk about in the next video. But also we will talk about graphs in great length since it's a large part of data structures and algorithms. A lot of data structures and algorithms involve graphs. So we'll be revisiting this idea, fairly frequently, and we'll discuss some different ways that we can, represent graphs and solve problems using graphs as well. So for now, this gives you enough information so that we can move on to trees. Thanks so much for watching. I'll see you in the next video.